Good morning, guys. So, I hope you have understood the chapter gravitation theory as well as a little bit problems we have dealt till the value of or problems topic which we have covered till G, right? We have talked about our questions during our live class regarding how acceleration due to gravity changes with depth and height, and we dealt with some problems. We have completed the theory of the chapter, but some of the sections theory only have been completed. We have not touched any numerical questions regarding it, right? So today we are going to finish off the entire chapter along with the numerical section. So the question first I want to do is this question: at what height from the surface of earth the gravitational potential and the value of G are this much value and this much value respectively? Take the radius of earth as 6400 kilometer. That is, at a perfectly, let's say any height h, the potential is found to be minus 5.4 into 10 to power 7, and some height h, G, is found to be 6. Then you are asked what is the value of that height h. So I hope you remember the value or equation for potential. It is minus Gm by r plus h. Why did I write r plus h? Because if this is earth with the radius r, we are finding the potential at a point h from the earth's surface. So V, potential, we measure from the center of mass, so it becomes r plus h, right? And similarly, what is the equation for G? That is Gm by r plus h whole square, right? That is a general formula we can use. So you have two equations. Let us divide these two, guys, right? So Gm and Gm goes off and 1 by r plus h remains, right? That is minus 5.4 into 10 to power 7 divided by 6 is equal to minus Gm by r plus h. Then so you will have only r plus h, right? Clear? So, and there is a minus also, so this minus and this minus cancels off, right? So I can write 5.4 divided by 10 to power 7 is equal to r plus h, right? So let us find what is r plus h. You will be finding this value as around 9000 kilometer, right? That is 10 to power 3, so it will be 0.9, right? Or 9 into, clear, 10 to power 6 meter. This is in meter, I believe, right? So this much is clear. That is equal to r plus h, and r is taken as how much? 6400 kilometer. So h will be equal to 2600 kilometer. Easy, right? Now let me make this one as small so that I can remove this section easily. Now the graphical representation etc. have taken, guys, so that's why I told you that graphs are based on neat section. So let's do this problem. A body of mass m is taken from earth's surface to a height h, or a height equal to twice the radius of earth. The change in potential energy will be, right? So let us talk about initial potential energy, that is, let's say it is uy, right? That is equal to minus Gmm by r, that is on the surface, right? So when you are pulling it to another point, let's say final potential energy will be minus Gmm by r plus h. R plus h becomes r plus 2r, or I can write it as just 3r, right? So I'll write it as 3r, right? Clear? Now change in potential energy will be delta U, that is final minus initial, or I can write minus Gmm by 3r, minus of minus becomes plus Gmm by r, right? Clear? So you will get it as 2 by 3 Gmm by r, right? But the answer is not in capital G but in terms of small g. So let us multiply r denominator and numerator with r, so you get 2 by 3 Gm by r squared into m into r. And what is Gm by r squared? That is acceleration due to gravity, so you can just write it as small g. So you get change in potential energy as 2 by 3 GMR or MGR, which is option A. Clear? Right? Now let us move on to the next question, guys. So let me first rub this section off. Okay. 25th question. Infinite number of bodies, each of mass 2 kg, are situated on x-axis at distances 1 meter, 2 meter, 4 meter, 8 meter respectively from the origin. Right? The resulting gravitational potential due to the system at the origin is. See, this is something which you learn in maths, that is known as geometrical progression. Right? So before that, I will tell you what the question is. Let's say this is the starting point. So this is first, second position, third position, fourth, fifth, sixth, 7 and 8 meter. Right? Here you are having a 2 kilogram mass, another 2 kilogram mass. Then you are having 2 kilogram mass right here. So your positions, remember, 1, 2, 4, 8, right? So in this 8 mass meter also you are having 2 kilogram mass, right? So how would you talk about gravitational potential? This V is equal to minus Gm by R, right? So total potential, if someone asks you, it is minus Gm, that is this 2 kilogram. And how much distance it is from origin? That is 1, minus G m by r, this is a 2 meter, minus G m by r, this is 4, this guy will be 8, right? Minus G m by r, right? Clear? Right. So here I can take minus 2g as common, so I can write 1, right? Plus 1 by 2 plus 1 by 4 plus 1 by 8, and this goes on till infinity, right? Right? Bracket closed. Right. Now this is known as geometrical progression, right? That is, if you are having, see, this is geometrical progression means, see, 1 by 2, this is the second term, this is the first term. 1 by 2 by first term is equal to 1 by 2. This is the third term, this is second term. So third term by second term, 1 by 4 by 1 by 2 is again 1 by 2 itself. Similarly, 1 by 8 by 1 by 4, right? So they are progressing with the common division factor or dividing factor. Each term, when you divide it with the previous number, right, you get the same divisor, right? 1 by 2 divided by 1 is 1 by 2, you get the same number. Similarly, 1 by 4 divided by 1 by 2, you get 1 by 2 itself, right? So this type of progression, right, is known as geometrical progression. What this is called geometrical progression, or it is called geometrical series, which you will I hope you will learn in your what do you say, in your mathematics section. So currently I'm going to take you, or there are actually two types of progression, which is arithmetic progression and the geometrical progression, right? You will learn in your maths section, right? See, I will just give you an idea what is the difference between arithmetic progression and geometrical progression. Arithmetic progression and geometrical progression. See, an arithmetic progression, suppose I say a term like this, 2, 4, 6, 8, 10, like this. This is an arithmetic progression. Why? They are common difference, right? They are having difference common. The difference here is 2, here 2, here 2, here 2. This is an example of what? Arithmetic progression. Progression means it goes on. So this is an arithmetic progression, right? And when I say a series is geometrical progression, if their ratio is common, that is, let's say this is 2, then 4, then 4 by 2 is 2, then 8 by 4 is 2, then 16 by 8 is 2, right? So their ratio 4 by 2 is 2, 8 by 4 is 2, 16 by 8 is 2, right? So their ratio is common, which is 2. Here the difference was 2, I believe, right? So this type of progression is known as geometrical progression, right? That is, if the second term and the first term's difference and is equal to the third and the second term's difference, then it is known as arithmetic progression. In a series, if the second term and the first term's ratio is equal to the third term and the second term's ratio, then it is known as a geometrical series or geometrical progression, right? Clear? Right. So there are, in the case here, in the case of geometrical progression, right, any there must be a sequence, right? So sum of infinite terms in the case of geometrical progression is first term divided by 1 minus common ratio. Sum of infinite terms in the case of a geometrical progression is a divided by 1 minus r. That is what is required in this section, right? So in arithmetic progression, this is an arithmetic progression, sorry, this is a geometrical progression, right? And here there are infinite terms, right? Till infinite you have to find the sum. So minus 2 by g, a, that is a first term, 1 divided by 1 minus common ratio is 1 by 2 by 1 is 1 by 2 by 1 is 1 by 2, 1 by 4 divided by 1 by 2 is also 1 by 2. So the common ratio is 1 by 2, right? So you can find the answer as minus 4g, right? The answer is minus 4g, right? That is your net potential. Yeah, so the answer comes because you know this value. So that's why I do. So geometrical progression till infinite term. Now this is something which I'm also giving you extra, not there in your any part of this question, but I want to tell you guys. Suppose there is fixed number, that is first term is there, second term is there, and goes on like that. You are having n number of terms in the case of geometrical progression. I'm talking about geometrical progression, right? That is, you are having first term as 1, second term as 2, the third term as 4, and the fourth term as 8, then 16, right? Like then 32, like that you are having a progression, right? And let's say, okay, you are having till 32, or let's say 64 also I'm going to take, right? So like that, how many number of terms are there? 1, 2, 3, 4, 5, 6, 7. That means this is a geometrical progression with how many terms? It is having 8 terms. That is n. The number of terms here is 8, right? This much clear? So someone asks you the sum of these two. It is very easy to do. 1 plus 2 plus 4, right? It is very easy, not that much tough. But if the numbers are very complicated, there is a very simple formula to find the sum of n number of terms is equal to a1, that is the first term, into 1 minus r raised to n divided by 1 minus r, right? This is a formula for sum of n terms in the case of geometrical progression, right? So that is equal to, suppose in this question a1 is 1 minus ratio is 2, and how many terms are there? How many terms? 1, 2, 3, 4, 5, 6, 7. 7 terms divided by 1 minus r again is how much? 2. So that is equal to, this section will be negative. Obviously this is also negative, so you just need to find the numerator section. 1 minus 2 raised to 7, or right, sorry, so you know what is 2 raised to 5? It is 32. That much you have to know. 1 minus 2 raised to 5 into 2 raised to 2, that is 1, right? 32 into 4 will be there, right? 32 into 4 is what? 8. Then that is 1, 2, 8. So the answer will be 127, right? Numerator will be, see, 1 into minus 127 divided by minus 1, right? So you can write it as 127. That will be the sum of this many terms, sum of this geometrical progression. Clear? The first term into 1 minus r raised to n. Clear? This is something mathematics, purely mathematics. I just wanted to make sure you understand. Clear? So this is an additional formula I gave you. This is mathematics part, right? I taught it because I want to make sure you understand it also, right? I could have just told you this is the equation by hearted and just substituted, but that doesn't make any sense, right? Now let us move on to the next one. Okay, graphical representation, we have taken it. Now let us move to this one, 27th question. A particle of mass m is situated at the center of the spherical shell of mass m and radius a. The magnitude of the gravitational potential at the point situated a by 2 distance from the center. This is something which I have taken, guys, right? If I believe I have taken, I don't know. This is a spherical shell given. This is having a radius a, right? You are asked the gravitational potential at distance a by 2 here, right? Clear? So this is the mass here, right? So this capital M is the mass of the sphere, right? Particle, and there is a particle here also. Ouch. Now the particle M is here, right? So the total potential will be due to this mass as well as this mass, right? So the total potential, let's say the point is P, right? Is at P will be equal to potential due to the entire shell will be what? Gm by R, which is A here by this shell, and this shell will be, of course it is a minus time, but the answer doesn't have minus, so you need not go for the negative sign. Plus, then this guy will be having a potential of what? Again Gm by this one, having A by 2 distance, right? So you can directly write it as 3Gam. This will become 2Gm now, 3Gm by A. Easy. I want to do this question, guys. With what velocity should a particle be projected so that its height becomes equal to the radius of Earth? So you are asked with which velocity you should throw so that it reaches a height equal to radius of Earth, right? So obviously, just like the previous cases, we will do conservation of energy process. So on the surface of Earth, again, potential energy as well as kinetic energy, right? If you are throwing with the velocity u, that is been asked, right? So there will be kinetic energy which is half mv square, and at the surface of Earth you will be, that object will be having a potential energy of minus gmm by r. So I'm removing this plus, right? That should be equal to the final kinetic energy and potential energy sum, right? At topmost position it will be having zero kinetic energy because no velocity there, and the potential energy will be minus gmm by r plus h. Now height is equal to the radius of Earth, right? So I can write r plus r, or I can just write it as 2r, right? Now let me remove the zero section. Clear? So here I can bring this half m section, every m can be removed, so half u squared is equal to minus gm by 2r plus gm by r. This guy came over here, so I can write it as half u squared is equal to minus gm by, not minus, plus gm by 2r, right? So this 2 1 by 2 section cancels off this guy and this 2 goes off, right? Or I can write u is equal to root gm by r. Clear? Right? The calculation is very simple if you understand the logic, right? Now let us move on to the next problem, guys. This section, as we are going to deal with escape velocity section, etc. Right? Now, the ratio of escape velocity of Earth to escape velocity of planet whose radius and mean density are twice, right? So you're asked what is the escape velocity of planet as well as of Earth. Now let us talk, this is the Earth's escape velocity, that is root 2 gm by r. I hope you remember the equation, right? So here you have talked about density and radius, etc. So obviously you have to write mass in terms of density. So this is equal to root g divided by r. In place of mass I am going to write it as volume into density, which is 4 by 3 pi r cube into rho. Right? Clear? Right? Sorry. Now from here I can easily say, or I can remove an r squared term, right? This is r and this is r cube, so it becomes r squared. Or I can write root r squared will be r, right? The other terms are all constant, right? G is constant, 4 by 3 is constant, pi is constant. So can't I say that escape velocity of Earth is proportional to r root rho, right? Clear? Now similarly planet's escape velocity will be sure the radius are supposed to be into earth, right? Similarly, velocity in the case from a planet will be equal to escape velocity of planet will be equal to radius of planet into density of planet, right? So here I am supposed to write density of earth now, right? So you're asked what is the ratio. All right, now you are again straight away write it like this is equal to re sorry re rho e divided by rp rho p, right? Now what has been talked about radius of the planet, it is said that radius of planet is twice the radius of earth, so here it becomes re by 2 re, right? And told that the density is also twice, so it is rho e by 2 rho e, right? So I will get this as 1 by 2 root 2, that is velocity of earth by velocity escape velocity of earth by escape velocity of planet is equal to 1 by 2 root 2. Clear? It's easy. Sorry. Now let us move on to the next question. Okay, 35. A remote sensing satellite, right, revolves in a circular orbit of height 0.25 into 10 to the power 6 meter above the surface of Earth. If the Earth's radius is given as this much, so this is h, this is r, right? And acceleration due to gravity is given as 9.8 per 6 meter second. You are asked what is the orbital velocity. So I hope you remember the equation of orbital velocity. See, I'll tell you a small secret, guys. Escape velocity is root 2 gm. Oh, sorry, I write it as mg now. It's same itself, but it looks good to write gm. Root 2 gm by r plus h, right? H becomes, on the surface it becomes h becomes 0, right? In the case of orbital velocity, right, is gm by r plus h. See, so there is only a root 2 difference, or you can even write that escape velocity is root 2 times orbital velocity. You can even write like this if you want, right? Sometimes you can be given just directly orbital velocity, you will be asked what is escape velocity, right? You just have to multiply root 2, right? So moving on to the problem. So you are given or you are asked what is the orbital velocity. So that is equal to root of, right? But the problem is you are not given that much details. You are only given g and you are given h and r. So you have to change this equation, right? So let us do something like this. Let us require a r squared here. So I have multiplied an r squared here. So it becomes r plus h in here, right? Right. So what is gm by r squared now? Gm by r squared is our g. So this becomes g into r squared divided by r plus h. Now all the terms are there in your question. That is the root of g is 9.8 as per the question. R is 6.38 square divided by r plus h, that is 6.38 plus 0.25 will be 6.63, right, into 10 to the power 6. Clear? Then the calculation, right, you will get around 7.76 kilometer per second, right? This is how you're supposed to do the problem, right? Clear? Let us remove this section. Okay. Now the next question is of a black hole. A black hole is an object whose gravitational field is so strong that even light cannot escape from it. To what approximate radius would Earth have to compress to become a black hole, right? So again that means the escape velocity is such that it is the light cannot escape. That is the case in the case of a black hole, right? So that means the escape velocity is minimum equal to the velocity of what? Light, right? That is the situation when it has to become, right? So even suppose that is now the sun, our earth has become black hole, means even the light cannot escape, and light is having how much velocity? It is having c, or 3 into 10 to power 8 meter per second velocity. Even that is not to be able to be escaped, right? So what should be the radius of earth so that the light is not being escaped? Means the minimum velocity, escape velocity, minimum escape velocity should be equal to velocity of light, right? So let's calculate in that way. That is root 2 gm by r on the surface, right, is equal to c, that is speed of light. So I can write r is equal to 2 gm by c square, right? So 2 g is 6.6 into 10 to power 11 minus 11, sorry, into mass is around 5.98 into 10 to power 24, that is given in the question. C squared becomes 3 into 10 to power 8 whole square. So the calculation after that you will get, if the radius is 10 to power minus 2 meter, that is if the earth string so small that its radius is 10 to power minus 2 meter, then it can become a black hole. Or when it becomes black hole, its radius will become so small as that of 10 to power minus 2 meter. Clear? Right? Let us move on to the next question now. Now we'll go for the next pick. This one. A geostationary satellite is orbiting at the Earth height 5r above the surface of Earth, means the distance. This is easy. Time period, right? Time period comes up means t square proportional to, yes, r raised to 3 by 2. So I just gave you the thing. You guys can do it by yourself. Right, see, I told you there is a relationship between escape velocity and orbital velocity, right? This one. A planet is moving an elliptical orbit in closest to the sun at the distance r1 and farthest away at the distance r2 if v1 and v2 are the linear velocities. See, when it is moving means obviously in Kepler's law I have told there is a law of conservation of momentum, right? So L1 will be equal to L2, right? So L1 I can write it as mr1 v1 is equal to mr2 v2. I have taken this much, guys. So you can write v1 by v2 is equal to r2 by r1. So that is a section of actually Kepler's law section itself. Okay. See, a particle is of mass, this I will say just straight away, right? A particle of mass m is thrown upwards from the surface of Earth with a velocity u. The mass and radius of Earth are respectively m and r. G is the gravitational constant, g is the acceleration to whatever. The minimum value of u so that the particle does not return back to Earth. That is, you are asked what is escape velocity. See, even if this much larger section has been given, the question is straight away, you are asked what is the escape velocity. Alright. Now, the radii of circular orbitals of two satellites A and B of Earth are 4r and r respectively. The satellite A is having speed 3v, the speed of satellite B, right? Orbital velocity ratios, easy. That is, let's say this is v, right? So we can say g and m is a constant. So I can say orbital velocity is inversely proportional to root r, right? The distance. Right, so you can just, one is 4r and the other is r. Very easy. So v1 by v2 will be equal to root of 4r by v1. First guy is having 4r, no? No, he is having, he's having r. So this becomes r and this denominator will be 4r. So r 1 by 2. So v2 will be equal to 2v1. That is equal to 6. 2 into 3. Right, so this is a straight away question types, guys. It is very easy to solve these type of questions, so don't leave if you see questions from gravitation chapter. Now similarly 44, 45 or retention energy, straight away question, right? Satellite is moving, Okay, this ratio kinetic energy to potential energy. I have talked to you about the potential energy and kinetic energy, right? Okay, 46. Aha, we have done this one. Velocity, this was in the terms of what? Okay, escape velocity is the ratio itself now. So it's very easy. I believe you can do the 46 questions very easy. So which one we have to go for? Let us go to the next one. 48. This is a straight question. Escape velocity is 11.2 km per second. Earth's mass is increasing to twice its present value, right? And the radius is reducing to half, means how much will be the escape velocity? Simple. Escape velocity is proportional to root. You can remove 2 and g, so you can just mass and r, right? So you're told the mass is becoming what, twice, right? And the radius is becoming half, means this becomes half, so 2 goes off, 4 become 4 root m by r, or root 4 m by r. Root 4 is twice, so the escape velocity becomes twice. So this level. So let us go for the next pick. This will not come off, huh? Let us go. I'll take another pick like this. 51. Other questions are easy, guys. We'll do the 51st question and we'll wrap up gravitation's numerical section. A satellite in free space sweeps stationary interplanetary dust at a rate of dm by dt is equal to alpha v, where m is the mass and v is the velocity of the satellite and alpha is a constant. What is the deceleration of the satellite? Now, so see, if you know, I have taken, actually force is actually rate of change of momentum, right? So it is dp by dt, right? But it is talked here that it is dm by dt, that is mass is changing, that means velocity is constant. So I can write dm by dt, because p is equal to, I can write it as d by dt as mv, right? So it is dm by dt into v, right? Now dm by dt is equal to given as alpha v, so this becomes alpha v into v, that is I can write it as alpha v square, right? This much is clear. Now what is retardation or acceleration? This negative acceleration is equal to force by mass. So alpha v squared by mass becomes retardation. Retardation means I have to put a negative sign also, so this becomes retardation, right? So minus alpha v squared by m. Very easy question. Okay, now let us move on to the next chapter, because I want to complete the basic questions. Clear? So moving on to the next chapter, that is chapter 9, right? Clear? This one of the, again, the easiest, one of the easiest chapter. I say it is much easier than gravitation. Clear? Less numerical sections from this chapter also, right? Clear? Chapter's name is Mechanical Properties of Solids. Mechanical Properties of Solids. Right? In your textbook, I believe, that is in your SM, I believe solids and liquids are believed to be in one chapter itself. So in your textbook, which is both of them are different chapters. Okay. So mechanical properties of solids is a very small chapter when compared to the liquid section. And the problems as well as formula section is also very small area. Okay, so some of the terms you have to know before you go for the chapters. Of course, here you will be, what and all we will be dealing in this chapter is, you will be talking more about how a solid changes its shape, right? How can the change in shape occurs, how volume can change, how can the density would it change, right? So how different types of objects can be classified according to the change in shape, etc., length change, volume change, etc., surface area change, etc., will be dealt in this chapter, right? So the first term which you have to know while you're dealing with this chapter is called elasticity. So you are asked what is an elastic object, or if you say that an object is having elastic property, what do you mean by that? See, the property of a body, by virtue of it, it tends to regain or retain its original size and shape when an application of force is there, is known as elasticity. Right? This is an object here, right? I applied a force which is called deforming force. Because why should I call it as deforming force? Because I applied this force to deform this object. I want to change its form, right? That's why this applied force is usually called deforming force. So when I apply this deforming force, let's say the object shrinks, that is, its size decreased, right, and after the removal of this force, if the object regains its original shape, then I would say this object is elastic in nature. And this property of regaining its original size and shape when the deforming force is removed is known as elasticity. Right? And this deformation is called elastic deformation. Elastic deformation, because this deformation, once the force is removed, it goes off completely, right? And there are two types of substances, right? And so okay, before going to the elastic section, also there is another term which you have to know, which is plastic. And the property which is shown by plastic is known as plasticity. So what do you know about plastic? The substance, the same substance you are having, or the same, not the same substance, you are having a different substance, right? You applied a deforming force, and its shape change, that is, let's say it shrink like this. But once you remove the force, the shape doesn't comes to its initial form. That type of object is known as plastic. That is, the object cannot regain its original shape and size. That type of object is known as plastic, and that property is known as plasticity. Clear? Now in this chapter we majorly talk with or about elastic properties of objects rather than plasticity. So first topic, then the subtopic which you have to talk is elastic behavior of solids. Elastic behavior of solids. How does it come up? See, each atom or molecule, right, when you consider in a substance, will be surrounded by some other atoms, right? So there will be interatomic or intermolecular forces in between them, and at equilibrium position, this force is maintained as it is, right? Now when a force is applied, a deforming force is applied, the atoms and molecules, or which were initially at equilibrium, they were at a proper interatomic or intermolecular distance, right? So when you applied a deforming force, the atoms or molecules get displaced from their equilibrium position, right? That means there is an interatomic distance is changed, right? So when you remove this and deforming force, the interatomic force which was already existing between these atoms or molecules, they tend to bring back the displaced, see the displaced, suppose they were displaced to here due to the application of force. You remove this force, so the interatomic force try to bring the estranged atom back to its initial position, right? That is, you are bringing the entire substance into its initial position. That is what happens, or that is what is causing the elastic behavior of solids. Clear? That is, again I'm repeating, that is, initially there are, let's say, some atoms like this, and if you consider a molecule, that also is okay. They are having a proper interatomic intermolecular forces between them at equilibrium. So what you did, you applied a force to forcefully asking the each atoms to displace from their initial position. So obviously the applied force is greater than the interatomic force. Right. So once you remove this force, the interatomic force again brings the estranged or the displaced atoms or molecules to their older position, so that the shape is retained after the removal of deforming force.
right? So this and all detailedly was learned by Hooke, and he stated the example or explanation of elasticity, and that law is known as Hooke's law, right? Hooke's law, that is law stated by Robert Hooke, right? Now, before we go for Robert Hooke's law, there are some terms you have to know, which is stress and strain. Stress and strain. See, when a body is faced with a deforming force, the there is a restoring or and reforming force has happened, its shape has changed. So actually, you told, remember we told where basically how the elastic behavior is happening. You applied a deforming force, interatomic distance increased, and the nuclear forces or intermolecular forces brought the estranged atoms to its initial force, right? So that nuclear forces, or I can say those interatomic force, can also be called a restoring force. Why restoring force? They are restoring the initial shape, right? So there are two type of force which you learn now, which is deforming force and restoring force. What is deforming force? Which brings the deformation of the object. Restoring force are which helps to regain the initial shape and size of the object. This much clear? Right. So when a body is faced with deforming force, the restoring force is usually equal to the magnitude but opposite in the direction of the deforming force appears, right? So this restoring force per unit area is called stress, right? That is a technical term. I will tell you how to learn or understand it by a common sense, right? So what is restoring force per unit area? That is called stress. So stress is restoring force per unit area, right? Clear? And usually this force is applied, suppose this is a cross sectional area, the force is usually applied normal to this cross section, right? And that's why stress unit is n by meter squared, newton per meter squared, and its dimensional formula is ml raised to 1 t raised to minus 2. Very easy, right? So see, it is just like this. Here itself I will talk about strain also. See, just having a book, you want to study, or let's say you have to study this book, so your mother nags you to learn a lot. So that means what you have is you are forcefully asked by the mother to study in some time, right? That means, let's say they will say in 2 hours you have to complete one entire chapter. So you will get what is known as stress, right? So what is stress? The force, right, acting on you per unit area, right? For 2 hours, that is the only time you have given. So within 2 hours you have to learn, so you get a headache, that is a stress, right? So after you have accessed or you have been accessed by stress, what you get? You get headache, that is a pain, that is called strain, right? So stress is studying. After studying, you get what is known as pain, that is strain. Let us talk with the now physics. You applied a force over here, right? And its shape shrinked. After the removal of this force, a restoring force acts opposite direction. That acting force per unit area is known as stress, right? So if I can say in place of restoring force, I can even say it is actually the deforming force itself, because why? Deforming force and restoring force are having same magnitude but opposite direction. So now I am talking stress in terms of deforming force. So a deforming force is acting per unit area, so that is stress, right? So when you apply the force, didn't the object shrink? So that much change in shape, that is this shrinking of this object due to the application of stress, that shrinking is known as strain, right? Due to study you got headache, that is strain. So due to application of force you got a change in shape of the object, that is called strain. Clear? right? So depending upon different types or how the change is happening in the regarding shape, you are having three types of stresses and three types of strain. So first type of stress is called longitudinal stress. Longitudinal stress. So it is also having another term called tensile stress. Tensile stress. And their strain, respective strain due to longitudinal stress will be longitudinal strain, or you can say tensile strain. Clear? Right. So as the name suggests, right, if the application of force is causing an object to change its length, then that type of stress is known as longitudinal stress. Clear? Easy to know, right? So this is not very easy, right? Suppose there is a cylinder like this, right? Okay, let's keep that straight, that is better, right? Let's say there is a cylinder like this, right? I pulled it from both the ends like this. So what will increase? Its length will increase, right? So its length increases. Initially, let's say its length was L. Let's say its length changed by delta L, right? Clear? So this delta L is the change in length. This much clear? Right. So I can say regarding the tensile, someone asks you what is tensile strength means, that is called as tensile stress, or I can say it is actually longitudinal stress. So a cylinder is compressed by this, or I can say extended. Suppose it is same figure, I can talk about compression also. That is, this is a cylinder. I compress like this. I applied a force, so it shrinks, right? So again, the length itself is changing, right? So here I can say what has been changed, length has been changed. So what is stress here? It is force per unit area itself, right? So this is longitudinal stress. I can say it is longitudinal stress. Someone asks you what is longitudinal strain. See, strain is, okay, this one is very important. Longitudinal strain or tensile strain is equal to change in length by original length. How much the change has occurred when compared to its initial length, that is called longitudinal strain. Commonly, what is stress and strain? I am retaining, I am taking and again taking, because you understand this. Stress means due to a force or amount of force which is applied per unit area, that is called stress. Actually, stress is like pressure itself, right? So stress is how much force, it can be restoring or it can be deforming force, how much is just applied per unit area, that is not stress. Strain is how much change that much stress has caused by, right, how much change that can be in length, volume, whatsoever, with compared to its initial form, that is known as strain. Clear? So in longitudinal stress, it is again force per unit area, how much force you are applying, how in how much area, that is longitudinal stress. Whereas longitudinal stress is how much change has happened in the length when compared to its initial length, that is known as longitudinal strain, or I can say it as tensile strain. Clear? So as you can say, numerator is in meter, denominator is in meter. Hence, strain doesn't have any unit, no unit. Clear? So what is the unit of stress? It is Newton per meter square. Right? That is the unit of stress, whereas strain has no unit. Clear? Right? Now, the next term which you have to know is, the next type of stress or strain you have to know is shearing stress or shearing strain. Shearing. Oh, why it is not writing? Shearing stress, or along with it, I have to learn about shearing strain. Okay, it's very easy. I'll first tell with an example, then we go for the technical term, etc. See, you are having, let's say, or US, let's say they are having a deck of cards like this, and they have arranged one above the other. They are having a deck of cards. So what happens? I only push at this end. I can say that the deck will move in this way, right? The base section will not be that much moved, but the top section moves like this. The base will be like this, not like this, but little bit inclined, right? This is called applying a shearing force. I'm just shearing at the surface. Clear? So this force applying per unit area, that is known as shearing stress. Right? Clear? That is, this is only at one end, right? So what happens if I'm applying here one force? Similarly, let's say in the same example, let us say I'm redrawing it here, right? Let us say I'm pulling here, and here also I'm pulling, so this will be much more slanted like this, right? The deck of cards will be aligned like this, right? So here also what I applied is I am changing the inclination of that object. Of course the shape is changing, right? But the bottom area coverage is not changing, right? The same is happening here, but I would say the inclination is changing. This is an example of shearing stress, and correspondingly the change in alignment, that is known as shearing strain. Right. So to suppose in your textbook they have taken an example of cylinder itself. Right. It is initially having length L. Right. So what they have done is they are applying a force here, so that now the cylinder looks like this. So there is a couple of forces. So two equal and opposite deforming force are applied parallel to the cross section area. Right? Parallel to the cross section area, two forces are applied, and this is known as tangential. Right? Right? So that's why shearing stress is also called tangential stress, because you are applying it tangential. Right? This causes a small displacement, right, at the this section, the small displacement, right? Let's say this angle, if I want, I can take it as theta. Let's say this displacement is delta x, right? So shearing strain, right, shearing strain is equal to, this is the change, right? And what is the initial thing? It is the length L. So I can say delta x by L, that is called shearing strain. Right. So someone asks you what is theta? It is the angular displacement of the cylinder with respect to vertical. Right. Clear. So usually delta x is quite similar to value. If someone asks you delta x in terms of delta theta, you can take it as even arc length. Right. That's not much change. Clear. I hope you understood what is shearing stress. Right. Now, next section you have to talk about is hydraulic stress. The last type of stress and strain you have to talk about is hydraulic stress. And its corresponding strain is called volume strain. Hydraulic stress and volume strain. That is the third type of stress strain section which you have to learn. This is very easy if you understand with the example. Let's say, suppose you are having a surface like this. Right, so solid sphere, right? And let's say I'm keeping it inside a liquid which is having high pressure, means from the entire area there will be a very strong push on the surface, right? This is, let's say this is a bucket which is having high pressure liquid. You keep an object, solid object here. Don't you think this entire liquid will be exerting a very high force on the entire boundary? Yes. So that now this object will shrink, not the shape but its volume will be shrinking, right? Its volume will be shrinking, right? This type of shrinking is known as volume strain, because its volume is changing. And this type of stress is known as hydraulic stress, because it happens in liquid form, right? Because here uniform compression is happening from all the sides, right? Here the change is not happening, only the volume is changing, right? This stress is known as hydraulic stress, or you can say somewhere you might read it as hydrostatic stress also, but it is usually hydraulic stress, or it is also called hydraulic pressure. Right. So volumetric strain I can say as very easy. What is volumetric strain or volume strain? It is change in volume per initial volume. Right. That is volume strain. Clear? So these are the basic strain terms which I want to introduce before you go to the major topic, which is Hooke's law. Hooke's law. So what do you mean by Hooke's law? Very easy. Robert Hooke stated that stress is directly proportional to strain. This is the only statement you have to say. That is Hooke's law, very easy, right? Clear? So the exact statement you can go for your textbook. I would recommend you read the exact statement from your textbook. But someone asks you what is Hooke's law, it is very easy to remember it as stress proportional to strain. This is just like the example which I told you just now. How many, suppose you have a lot of thing to study, so you get have to, obviously you have to learn that in a fixed time, so that means you are going to have a lot of stress. How much stress you are going to take, that much pain in your head, that is that much will be the increase in pain. That is how much stress increases, that much strain you are going to have, right? So that's why you can say stress is proportional to strain. So in order to remove that proportional sign, you can write it as stress equal to K into strain, right? This is called, K is called modulus of elasticity, or you can say elastic moduli, right? And there are different types of elastic moduli which will be learned, or which I will teach you later on, right? So K, someone asks you the definition of elastic moduli or modulus of elasticity, K is equal to stress by strain, right? And this modulus of elasticity depends upon what the material. That is, if you have a iron bar and you have a plastic bar, both of them will have different type of modulus of elasticity. So even if they have the same length as well as area, etc., it depends upon the material. So stress is directly proportional to strain, that is Hooke's law. In order to remove that proportionality, constant was introduced by Hooke. That K is known as modulus of elasticity, or elastic moduli, right? So if you want, I can write the no, modulus of elasticity or elastic moduli. Clear? So this much is the only thing which I want to take today, right? So what and all we have completed regarding the new chapter. We have dealt with basically a lot of ideas, right? Actually, good news, we have completed half the chapter. That much short the chapter is, right? So we have talked about what we majorly talked about, what is elastic material, right? So what do you mean by elastic material? An object which can retain its shape after the application or after the removal of applied deforming force. That type of object is known as elastic object, and the property is known as elasticity. An object which cannot retain its shape after the removal of deforming force is known as plastic object, right? So these are two extreme objects, right? So plastic objects, the objects which are showing plastic nature, so I can say that property as plasticity, and the objects which are elastic shows elasticity property. Right. Now in molecular way, how does this elasticity can be explained? If you consider an object, there will be a lot of molecules and atoms inside them, and each atom will be having intermolecular forces between them. On the application of a deforming force, the distance between the atoms increases as the applied force will be greater than the intermolecular forces. So once the forces are removed, the intermolecular forces again acts, hence bringing the atoms to their initial position. That is why the objects which are having elastic nature gets their or retain their shape. So plastic objects, the problem what might be? The problem is their intermolecular forces are very weak, that they are not able to bring the displaced atoms to its initial position, right? And this etc can be explained by Hooke's law, right? So in order to lead to the Hooke's law, we have to talk about a lot of common terms which comes about again and again, which is stress and strain, right? So force acting, that can be deforming force which is equal to but in opposite direction as that of the restoring force per unit area, right? And the stress what brings about is known as strain, right? That is change in some parameter per unit, the original parameter. Clear? So there are three types of stress strain which you have learned. First one is a longitudinal stress, which is also called tensile stress, and its relative strain is tensile strain. Then the shearing stress or shearing strain, clear, or it is called tangential stress or tangential strain. And then there is hydraulic, right? Hydraulic stress and hydraulic strain. We have taken it in detail, guys. I would recommend you guys can listen to the video and write it as the notes by yourself. Clear?